So, any questions from the last class? That's a routine question any teacher asks at the beginning of a class, right? And mostly the answer is like an airy silence. No one says anything. Fine. So, what we will be doing today is kind of a generalization of this majority finding. As I go along, I can state this problem both in terms of an array as well as a stream, because it works in both the domains. Whatever I say, that would kind of work if you have a sequence, that means a stream, or else if you have an array. So, I might state the problem both in terms of an array or a stream. So, what in majority, what was your goal? Looked at an array and tried to find whether there existed an element which had a frequency more than n by 2, right. And you saw that even solving it in streaming in one pass was not at all easy, right. Okay. So, the generalization might be for this problem is that the user gives you a parameter k, right, and you have a stream or array whatever say of size n, and you want to report or count whatever the frequency is more than n by k. Now, k roughly 2, you have the majority problem, right. So, this is the goal. Now, as your Monday's first lecture would be on, in a few of my lectures I have been talking of impossibility results, right, because the moment you take away power from your machine, right, your RAM model had this power of jumping here and there, like whatever data it requires it can go and fetch it in some constant time, right. So, it had more power, but in streaming, as we were discussing over last few lectures, you do not have much power, right. And then impossibility results become important, that what all you cannot do, knowing that is important. So, one can prove a impossibility result. Impossibility results in this for the streaming framework would be Monday's first lecture, and probably the Monday's tutorial would also be on that. So, there you would have an idea on how you prove this kind of impossibility results in streaming. So, the impossibility result in here is that without a linear space you cannot solve this heavy eaters problem for the streaming problem. Fine. So, what we would do is, the moment we have this impossibility result, then we say that fine, this is what we have to do.
of size k,
Hmm.
and
But then you have to count, no? You have to, something comes and then you might have to drop.
yeah, so like for majority we maintain one count.
But k can be, k can be anything, right?
Sorry,
K can be anything.
k can be. I see. So when you say impossibility for arbitrary k,
Yeah. So it should be max of n and k, mean of n and k, right? Okay.
also the frequency is strictly more than n.
Yeah. Oh, I think I should. Yeah. Yeah, I should be careful there. Now, so getting into approximate heavy heaters, there our life we would kind of reformulate the problem in the following way. This will use hashing in a way. So, what you have is now a k, you now have an epsilon, this is an user parameter and you have this string. My goal is again to report elements having frequency greater than n by k. Now, as this was kind of a difficult problem, so you would work in this setting that k will be much less than n, and see the point is now say you have some elements which have frequencies more than n by k. These are your kind of heavy heaters. Now, my algorithm would not see what should I call a good approximate algorithm for heavy heaters? It should not should not miss any element whose frequency is more than n by k, right, as people would say this in terms of, so no false negatives, right. Now, in doing so, as it has to take care of the space, it might, by the way, anyone in here knows what is a Bloom filter? Anyone in here knows what is a Bloom filter in terms of hashing? It's a data structure that answers membership queries, right? Membership queries on site. So, the data structure that you design in here would be close to what you encounter in Bloom filters. Okay. Anyway, so the idea in here is you should not miss any element which has this required frequency. So, this is one side of the story. What is the other side of the story? That it should not be fooled by anything in here. Numbers which have I have not specified this quantity as yet, maybe we will do later on. So, numbers which has significantly lesser frequencies, I should never report them. But as I would solve this problem with very less amount of space, numbers in this zone I will report. So, that is kind of the trade off. So, the algorithm when we kind of go through it, you would understand that, see, what would be an efficient data structure for this thing? That data structure should be able to squeeze this zone of uncertainty as much as possible, right, this zone as much as possible. So, if you can make it very crisp, you are doing good, but again that would come at a cost of a space. So, therein comes this parameter epsilon, right. So, this is the approximate. I mean, what I meant by approximate was this, that some zone, nothing, if an element has a frequency in that zone, it is never going to be reported. If it is surely greater than n by k, sure, but there is a zone in between where this number should come. The reason this would happen is, as you would see later on, I would use hashing very strongly. So, what I would do is, I take this universe, map it to a very small size space. Now, if this hash function is kind of this good hash function, which probably Venkatesh discussed yesterday, and you do some tutorial problems today. If this hash function is good enough, then what it will do is, it will kind of distribute uniformly these numbers within that range. But what you cannot escape is multiple items from the universe mapping into one location, right, and that would possibly increase the. So, what I would do is, I would kind of take these elements hash, multiple elements here can go to the same location. Now, what will happen that? What will then happen? Whenever I make a query with a new element, I can hash and go to its location, but the problem now will be, there will be many other elements which has hashed to that location, and so the frequency count of that element would show to be more than what it was, and the elements responsible for pushing up that count is elements in this zone. Fine. So, this is one side of the story, that if I can have a bucket, can have kind of. So, someone was talking of hashing in one of my lectures, possibly yes, the person at the back, and I told the story of don't fire cannonballs for mosquitoes. Now, so where do you apply hashing? Where do you apply hashing? Do you have an idea of, after attending Venkatesh's lecture yesterday, where do you apply hashing? Hashing is a very, what should I say, a very powerful and precious tool. Don't use it anywhere you like. The first thing is, you have to come down to a very small, your universe has to be mapped to a very small location. That is primarily one of the reasons. The other reasons comes from, spreading things uniformly, so that there are no collisions, or you want to minimize collisions as far as possible, so on and so forth, right. So, here is a particular case. Now, what we saw was, if you want to compress space too much, there is this possibility of error shooting up, right, because there may be many elements mapping to the same location. How can I possibly reduce this? By now, you know a probabilistic tool that allows you to reduce errors. We have seen its example in the last few lectures. Make independent trials, right. So, what I do is, instead of one array, instead of a single dimensional array, I keep a multi-dimensional array, right. So, one is this bucket size, the other is the number. So, I will fix, my calculation should fix to me what is the number of independent trials that I need to run, And now by now you have this idea that the amount of error that I, so I obviously want to keep the error down, right, but keeping the error down means running more number of independent trials. So, this epsilon and a delta, so this will again be an epsilon delta algorithm. So, this epsilon and delta would fix the bucket size as well as the number of times you run the independent trials. So, this data structure that I am going to discuss for you is going to be a 2-dimensional array whose one dimension, the buckets, so the indices to which your hash functions come will be determined by this epsilon factor, the error that you want. There is another error on the probability side, that is the delta thing, that would dictate, or rather 1 by delta would dictate the amount of independent trials that you need to make. Fine. So, any difficulties with this high level idea? Now, I would get into formalisms. This lecture goes up to 12:45, right? Yeah, okay, fine. Okay, so I have this. Now I call this to be epsilon heavy hitters. So, my input is say a string sigma. I have k to be a positive integer parameter. I have an epsilon, which is kind of the error parameter. Now, let me fix this. I have missed this region. So, this should be nk minus epsilon into n. Okay. So, this is epsilon, the error parameter epsilon is used in the following way. Okay. What is our goal? So, you by now understand what I mean by high frequency elements, the ones having more than n by k, whose frequency is greater than n by k are not missed. Second, as I said, so some more are there, which are there. So, this is my goal. So, kind of I have come down in my expectations, right. Earlier I was just report only those elements which are greater than having frequency greater than n by k. Now, I say, well, also report this. Now, whenever you talk in terms of a data structure, So, I am going to design a data structure for you. So, how do you design a data structure? What dictates the choice of a data structure, right? So, so say for example, you are doing a binary search. What kind of data structure should you use? Array, right? Should you not use a linked list? You can. Can you? Maybe. You cannot. So, in theory it is always difficult to have different answers existing at the same time. So, we need to rule one of these answers out. So, if you have a linked list, you can go only in, right. So, that means the problem at hand dictates the choice of your data structure. So, when you design a data structure, you should be very clear in your head what are your requirements out of this of the data structure. So, this is one thing you should keep in mind. So, this should tell you what are the operations, what are the fundamental operations that you need on this data structure. Number one. The second question that you should ask yourself is whether the data is static or dynamic. Right? Static means you are given the data at a time, it is not going to change during your run of the algorithm, and dynamic is when the data might change in between. So, if you this is a thumb rule that if you keep these two in track, you would be well in your pursuit of a good data structure. Okay. So, the operation that I need in here is whenever an element, a new element comes in this stream, I have to increment its count, because I am counting frequencies after all, right. So, increment is an operation that I need to support, number one. And the second was, as I said, my goal is to report frequencies. So, that means if there is a query that given an element in the stream, give me its count. What is the count of the element? That means return the frequency. And by now you understand that what I am returning is an estimate, not the exact frequency, and this estimate is always going to be an overestimate, right. Because for any element, what has happened is many other elements has added on to its frequency, fine. Okay. So, there are two operations that I need to support. One is this increment x, and the second is count x. Now, like say for example, when you design your search algorithms on an array or a binary search tree, you have specific operations that if this happens go left, if this happens go right, so on and so forth. So, we need to fix those things for these two operands, increment and count. So, the increment thing is not going to be much difficult, right. What do you do? Take this element, let it go through a hash function, find its position in the bucket, increment the count. Pretty simple. Okay. So, as I said, the data structure would be a two-dimensional array. So, this is B, so the number of buckets, and say this is your okay. So, this is your two-dimensional array. As I said, this comes from hash, and these are your comes from your independent channels. Okay. So, this is for compressing stream sigma using a hash function from u sorry okay. Now again I try to convey this idea to you that what this hash function should be, how much independence it should have, is primarily dictated by the proof of the theorem, right. So, like we saw yesterday that I wanted this covariance term out, and so I wanted two wise independence, right. So, that would actually dictate what kind of independence I require from the hash function. Fine. So, this hash function, what it does is takes an element of a stream and you hash to one of these locations. So, what I do is I have let me index these hash functions with hi, where I equals to 1 to L, and hi's form independent channels. So, each hash function has a level of independence in it, 2 wise, 3 wise, k wise, whatever it is, but L of these hash functions, they are again independent of each other. Right. Now, what you do when this increment comes, what I will do is I will hash to a particular location of the bucket, right, and then what I will do is run L of these hash functions, right. So, it will take me to different locations and then I will increment a 1 there. So, let us go through this, what this increment operator does. Can I fit it in here? Yeah, maybe I can fit it in here. So, what this is doing is adding plus 1 in these locations. Run L independent copies. Now see what is happening for an element. So, you fix a element in your stream, say an element A, that one you pass through. So, now focus on a particular HI. So, let this x be some A. So, when this A came in the stream, what you did was you made L independent hashes of this A, right. It went to some location in the bucket, and wherever there was a plus 1, you incremented them. So, this A was gone, then some B came, it also went through it, it also added things in the array, right, and this kept on happening. Somewhere down the line, you query about the frequency of A. So, when you are querying about the frequency of A, this is all about how many times prior to this increment A was called, that is the count of A. So, there is an exact count, fine, but what has happened in between was there were many different B's not equals to A that has probably made an overestimate of this. Now when your query A comes, again you hash, go to a particular location of the bucket. So, you know that A is in this position of the bucket, in this column, and there are L independent trials where there were many B's not equals to A's that has added up to this counts. Now, if you are to design this count A algorithm to return its frequency, what would you do? So, the moment you have a count A and it goes through the hash function, you know where it goes, then what do you do? You would obviously need the minimum disturbance to the count of A, right. So, look at those set of elements that has disturbed the count of A, that has not disturbed the count of A the most. So, the idea is to then take minimum, right. And by now Uddalak has taught you how to handle this max and mins over random variables using either your union bounds or intersections, right. So, then you handle it probabilistically in that fashion. So, this is the idea. So, let us fix that. So, before I get into the before I as I said, just to fix this data structure we need to fix this too. So, this is done, we are now focusing on this. So, is this increment part clear, right? Running independent trials on the same element. Okay, so, before I go deep into that, let me make an observation that counters are never decremented, which implies that fx frequency of x in sigma is so fx is always less than so it means we always have an overestimate. Where does this overestimate come from? So, that we have to fix now to fix our count, to fix the algorithm for the operation count. Now, see, one good thing about this, before I get into this analysis, let me point out a few things. If it is so that I can almost make this data structure not dependent on n and m, right. I mean, when I am counting frequencies, I am counting up to m. So, a log m is anyway obvious, because I have to count frequencies, right. So, my stream was like A1, A2 up to AM, and if I count frequencies, one element can have almost m. So, log m, when I report to you a frequency, log m is kind of needed. So, this log m plus log n thing, that is obvious in streaming, you understand by that by now. But the rest, if I can just make it independent of n, then I am really doing very good, right. Because whatever your n might be, I can make this array size totally independent of n. But the elements inside, when I want to count those frequencies, that would depend on, because you need bits to count, to maintain those numbers. So, that would be dependent on n and m, but again that is a logarithmic function. So, this is actually a very powerful data structure. Now, when I move to the, I will just quickly finish off this. In the next, we will see that we will try to simulate almost the same thing using only a single array. I will not even have this multiple rows. So, that would be count sketch. So, this data structure is actually known as count min sketch, because in the query I will take a minimum over this rows for a particular column. The next algorithm that we would discuss for this epsilon heavy hitters would be count sketch, and there the fun is you have to do it in one dimension. So, that means you are not allowed independent trials to push down the error. The question is then, what do you do, right? So, start thinking about this in your background. So, we will come to that, but the challenge is, if I am to get down to a less space, instead of a 2-dimensional array, if I want to come down to a 1-dimensional array, what do I do? Because then I cannot take recourse to independent trials, fine. Okay. But you can answer this question if you have understood what is actually going on around here. I know that there are L different estimates of fx. Right. Whenever you had x, you hashed on to that location and you had independent trials. So, you have L different estimates of fx. So, your count x is pretty simple. So, you look at this name, actually CMS I am writing actually means count min sketch. So, this algorithm is very popularly known as count min sketch. right. So, that is what I said, take the minimum among these independent trials, and this is what you return. So, CMS is this array. So, what I do, I get an X, hash on to that location for I many times, look into those rows, take the minimum. Okay. So, I fixed these two operations on the data structure, that is what I needed. So, now it is done. Okay. So, now what I would do is, I would not give you the full analysis, but I will just give you an idea of the overestimate that I am making. So, where from, yeah, you had some queries, yeah. Scroll down, okay, okay. I write too much, right? There was a complaint yesterday. There was a complaint from one of the students that I write too much. And then I said that not much material is around, so this might help you if I write. Anyway, the slides are being given, no, Professor Somasundara? Yeah, I think these things are shared with you, right? Right. Now, if you look into the overestimate, did I keep the pen? Yeah. So, this overestimate comes from where? So, it comes from a set of y's not equals to x such that, right, now can you say anything about this set? Now, if you look into this set S, what has happened is, this set is dependent on your choice of the hash function. How was your hash function chosen? Uniformly at random from the set of hash functions. So, that means this S, set S, is the outcome of a random process. So, if I look into any particular element of the array that is related to x, this counts fx and plus does something. What is that? It adds these frequencies. Right? I do not, in the summation I do not write y not equals to x, because my set S is defined in that way, right. So, this is the, these are the bunches of y's that would add up to the count of x, fine. Now, see this frequency, whatever was kind of the quantity in the frequency that was pushing up the value, dependent on S. So, that quantity is also a random quantity. Who dictates that? Your choice of the hash function. Now, if your hash function was really good, then this x or y should have been uniformly distributed in the range of the buckets of size B. So, what was your hash function doing? Taking this universe U, mapping it to B. Now, the probability that if you pick any element x or any element y, that it would go to any location, a particular location, is uniformly at random. So, that is kind of a probability of 1 by B, right? Because you have B buckets. So, if your hash function is good, I can write this as and then you can write this as n by B. So, you can write, I mean, I am kind of maybe hand waving a little bit, but so you can write this if, as I said, if hash functions are good. You understand what I mean by good. Now, the trick is you set B to 1 by epsilon. So, you have now bounded your overestimate by Fx plus n by epsilon. Mind you, that zone was that thing only. So, no element will get into the count whose frequency is low, because it cannot now cross the barrier of. So, think of this, think over this frequency line, right. What I have done is, for each element given you an overestimate. Now, I would have been in problem if an element in here being overestimated landed up there, I would have counted it. But this small calculation that I did for you, and in which the random choice of the hash function, these good hash functions helped me, made it sure that no element here, this element here would also be overestimated, but it would not cross this barrier, because your overestimation is by an amount of epsilon n. Here is that quantity sitting. So, that was the trick in the choice of B. So, that is 1 by epsilon, and an analysis which I had not get into is the analysis of the error, which would actually give you the fact that L would be equals to roughly order of log of 1 by delta, and your B is 1 by epsilon. B we have seen why. For this L to be log of 1 by delta, I have to get into the error analysis, which I am skipping for now. But again, the same kind of Chebyshev argument would work. But here there is a minimum thing which you have to handle very carefully. So, minimum would translate to an intersection, right. So, intersection, you have independence, so you can look at products, each individual to the power of L. So, you will get to the power of L, and that is why you have a log term there. Right. So, this is what count mean sketch is. Any queries before I move into count sketch, where I will try to do the same thing using only a one dimensional array. Any queries? So, by now I think you can appreciate the power of independent trials. Now, if I am given only a single dimensional array, how I would simulate this is going to be a challenge. What do I do? Hey, if your queries, ask, or you have an idea, throw it out. Yeah, tell me. Variable bucket sizes. So, you want that would be a problematic thing. No, I have to hash. So, you think of this. Your idea was possibly good, but you think of this. This bucket size has to be prefixed because I am hashing from a universe to B. So, if you change this index and x which was being hashed to a 100th location earlier might now hash to a 110th location, and then you are done, you are gone. So, B has to be prefixed. Once your algorithm, this epsilon delta parameters are given to you, this B has to be prefixed, because you cannot have a variable array, right. Then what? The only possible thing that might help me is as follows. Say I have an element x which gets through this hash function, this suitably chosen hash function gets to this location. Now, by now you know that there would be y not equals to x such that hy is equals to hx. So, this element y would also in fact there would be many such y's. So, let me mark them as y1, y2. So, there will be many such yi's which goes and disturbs the frequency of x. And as I am using only one unidimensional array, the only thing that can possibly save me is, what I would try to do is I would look into these contributions from this yi's and kind of attach a plus minus 1 random variable to it and hope that some of the contributions from yi's would push up, some of the contributions from some other yi's would pull down, such that this entire sum would be equals to 0. So, I would think of attaching this, instead of adding up or taking minimum, what I would try to do is make these contributions that all other yi's make random, kind of plus minus 1 random, so that some of the frequencies add up, some of the frequencies subtract, on the expectation everything goes to 0 apart from the count of x, right. So, that is the idea we will try to implement. So, let me call this array CS and let its size be some k, you initialize initialize this array elements to 0 as you start counting. Now, you have seen that in the case of count means sketch, the array size was 1 by epsilon. Here if you go through the analysis, this array size would be the size of the array in the one dimensional thing would kind of grow up because your epsilon is less than 1. So, this cannot be avoided, right. Again as I said, so I showed you for count means sketch how this 1 by epsilon thing was coming, right. How you remember this, right? This overestimate calculation actually was dictating the size of the number of buckets, the number of columns that you would have in the data structure, and the probability error was dictating the number of rows. So, in here what will happen is this overestimate thing, as because this is a unidimensional array and these epsilons are less than 1. So, you cannot but escape this 1 by epsilon square thing, right. So, again as I said, this calculation should dictate this 1 by epsilon square, and then what I do is I have, instead of one hash function, random hash function, I take now 2 random hash functions. Again my calculation would kind of fix the amount of independence that I require from the hash function. Choose another random hash function gn to plus minus 1 from a okay. Ensure one thing, ensure that the choice of G and H has nothing to do among themselves. Okay. So, what you now do, whenever you see a token, so J belongs to this universe of size n, remember. What you do is for this array CS, you go to that location, so now it is no longer an increment, it is an addition of a random variable which can be either plus or minus 1. This might even work if the token has a weight, so you can multiply then the plus minus 1 with a weight. So, it would even work for weighted case. Anyway, so this is what I do. So, this is actually my increment step. Earlier what was just adding plus 1, Now it is adding a random variable plus minus 1. Okay. So, what is my output? Now, in output I need to be a little bit cautious, because it might so happen that the quantity whose frequency I am wanting to count has gone through a very precarious sequence of updates, such that this has always been minus 1, right. So, the output also cannot be whatever is there in the array. I have to also make it go through a multiplication with this GA, right. Why? Now, think of this. If this GA for a particular, I am not looking at a particular token. So, this GA is equals to say minus 1. Now, if on the output side I multiply it with GA again, then these two minus 1s should make it a plus 1. And if this was anyway plus 1, then that would also be plus 1, and then you would be doing fine. So, that is the idea. So, on output side what you do is, so this is the trick. The entire fun actually lies in this. Without this multiplication, I could not have proved unbiased estimator, which I will shortly do. So, what is the situation now in here? If you think in terms of the array, so you have this array CS, this count sketch array for a particular element I, say you have hashed it to a location say HI, and there are J1, J2, many such say JKs, such that HI equals to HJ1, HI equals to HJ2, so on and so forth, HI equals to HJK. And but what we have done is, this contribution that gets from J1, J2, Jk, they come with some with random plus 1, some with minus 1, right. So, all these contributions that go, they are not just a simple plus addition, they can be a minus addition, and you hope on the expectation they kind of cancels out. So, is the idea clear? Fine. Now, let us get into the analysis of the overestimate. So, fix A in sigma, and so let x be the random variable denoting the frequency estimate, now I fix an indicator random variable for all other tokens apart from A, which is equals to 1 if the hash value goes to A. the rest are all 0 because I do not need their contribution. So, for each token j in n, so let now notice this random variable. If it is a random variable, see now in the analysis we have to be little cautious because now there are two sources of randomness, a randomness coming from H, a randomness coming from G. I have to be very particular about it. So, this randomness on the variable yj is coming from where? H, right. So, this is the source of randomness for yj. Fine. So, now I look at a token j. When I say contributes, it can mean either a positive contribution or a negative contribution. To the counter Cs HA, if and only if now what is the amount of the contribution that we have to fix? That is Fj, whatever is the frequency of j, and that comes with a, right, because whenever you are looking at a token j, it goes through a hash function g, so it either adds +1 or -1. So, this is the amount of contribution that the token j is giving to that particular location. So, what is your x? The final frequency. Mind you, x has contribution from A as well as different j's such that those j's had been hashed to this location of A with some random signs. So, that is j into gj, and I am only bothered about those j's whose hash value is equals to the hash value of A. So, that means this random variable takes care of that because those don't hash has 0. So, I am done. Which one? Okay. So, what I am now looking at is, I am looking at a particular location of this array where I am trying to argue about the frequency estimate for a token A in the universe, right. So, you have fixed a token A. Now, this token A through this hash function H has gone to a particular location of the array. Now, I am looking at all other tokens in this stream that has also gone through this hash function H and has gone to the same location. So, this fixing the locations is taken care of by this indicator random variable, fine. Now, if you look into all those j's which has gone to the location of A, what is this contribution? It comes with its frequency, but not with its exact frequency, but multiplied with this random variable plus or minus 1, right? That was my algorithm. Remember? Go back to the algorithm. It came with this contribution. So, each time you are adding either a plus 1 or a minus 1. Agreed? But am I fully correct? No, no, this is j equals to 1 to n, a is within that. No, a is there, right? This is j equals to 1 to n. So, I have taken everything. See, once you have fixed a token, this has hashed to a particular location. When it has hashed, it has gone with its sign, random sign, and that has been taken care of in here, right, because j equals to runs from 1 to n. So, a is in there. But the thing that I have missed is when I reported for a, I not only reported this, but I also reported this random value GA, right. So, my estimate is actually GA into this. Now, see what has happened actually in this particular location corresponding to A, many other tokens have contributed with plus minus whatever. So, finally, there has been a value in there. Now, when a query has come for A, my algorithm says, so what is my algorithm now telling me? Telling me that look into that location, whatever the value is in there, plus minus whatever, multiply it with GA and then report, right, and x was the random variable capturing this value. So, x should be this. So, this is the full contribution, this part is this contribution in this CSHA, and this is this random variable GA with which it was being multiplied. Done? Right. Now, let us analyze this quantity. Now, first, so this is over j equals to 1 to n. So, let me now write this quantity as, so this x is for a particular a, right, for an a belonging to sigma. Now, what I am trying to now do is write this random variable as contribution from a and from the rest. Now, see the fun thing will happen. So, this sum is on j's which belongs to n minus a. So, the rest contribution, right. So, from this universe I remove a. So, this remains whatever it is, fj into gj into yj. But for a, what are you getting? It's now become GA into FA into GA into 1. What is GA square? 1. That is the reason I took this random variable to be plus minus 1. The fun is actually there. So, this quantity is GA square into FA, right, because now j is equals to a and yj is 1, right. So, this is nothing but FA. That was the reason I multiplied it with G. So, the contribution of FA will never come out as negative. The rest will come out as plus minus randomly and sort of cancel things out. Fine. Now, you start getting the fun of probability, right. You can do a lot many things. Okay. Now, let us even analyze this further. My final goal is to show that this x is an unbiased estimator. Oh, I do not have much time. So, I will not get into the variance part, but let us just show that this is an unbiased estimator. So, that means I need to show that this is what it was supposed to count. Okay. Now, so what I am taking is expectation on this x. Now, mind you, what is FA? This is not an estimate. FA is the exact frequency of A. So, this is a constant for my case. Once you fix a token, its frequency is what it is. Okay. So, an expectation of a constant is constant. So, this is FA plus I use linearity of expectations. So, use linearity of expectations on this. I think I missed a term there, right? Oh, ho, 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 ho. You should have told me. I missed a term in here. See, in this contribution from rest, this was a sum multiplied with GA, right. I took the contribution of GA in this sum, but I did not take it for the other one. So, this is actually right. So, there was a GA outside which I missed, right. So, this was an error. Okay. So, you are taking expectations over this. Use linearity of expectations. Now, see, these FJs are constants. So, the frequencies are what they are. For this sum, GA is also a constant, because in here this is for all J's minus A. So, A is a constant for it. So, you now look at a term which is a product of now you are in a situation where you have to take expectation on a product of two quantities. One quantity is dependent on the randomness of G, and this, as we argued earlier, dependent on H, and initially I made H and G independent, right. So, now I can write this as the product of their individual expectations. Okay, let me not just write it just in one go. Now, so focus on this term, expectation of G of j into Yj. So, this I can write as expectation of Gj into of yj. So, this is true for all j's not equals to a, fine, because your sum is indexed over all j's not equals to a. Okay. And why is this? Because g and h are independent. Now, what is this expectation? This expectation, what is this? This was, g was a random hash function between +1 and -1. So, it was spreading all elements j in your universe uniformly to 2 locations plus minus 1. So, you add them up, that is your expectation. So, this is 0. So, whatever this expectation yj might be, this entire quantity is 0. So, that means each such product is a 0. So, the entire sum is 0. So, this entire thing goes to 0. So, what you land up with is Fn. So, this is an unbiased estimator. So, I would stop here. One can even do little bit more involved calculations using these facts to show that your variance is also nicely bounded, and you can get to a epsilon delta rather an algorithm which is like just fit for this median of means trick. And finally, one can show that now with the requirement of space 1 by epsilon square log of 1 by delta log m plus log n. So, this is your final space, right. So, I would stop here. Queries. So, variance would be even more fun calculations than this one, right. So, do not you find this algorithm to be nice? So, it nicely uses probability. So, the entire trick actually was dependent on that random function g uniformly distributing any token to either +1 or -1, and it was taken care well by this multiplication of GA. Yeah, any queries? You have none.